The purpose of these videos is to review each one of the 6 big ideas from the AP Chemistry curriculum. In each one of these videos, I'm going to cover all topics and concepts and key terms related to each video, but very quickly. There will not be very many practice problems or opportunities for practice with the content, but just more of a refresher of some key terms and ideas so that when we start actually reviewing and do practice problems, you have some notes to reference. So, big idea 1. Part 1. Big idea 1 is going to be split into 2 videos. In this first video, we're going to talk about atoms, elements, and matter. So on our periodic table, we have all of our elements. The number on the top, remember, is our atomic number. Remember, our atomic number tells us the number of protons in an atom. The number on the bottom is the average atomic mass, which is equal to the average of all the isotopes of that atom. Remembering that isotopes are atoms with the same element, so the same number of protons, but different masses because they have different numbers of neutrons. So forms of this that can be expressed, we could have fluorine 19 and fluorine 20, where each one of these is the mass of those 2 isotopes. Where does the mass come from? Well, the mass we know is equal to the number of protons plus the number of neutrons. And then this average represents the average of all of these isotopes and their percent abundances that exist in nature. How can we find those isotopes experimentally? Well, there's a technique that we talked about called mass spectrometry, which is a technique that's used to take any sample and identify the mass of the atoms or ions or molecules that are present in that sample. So here we go. We have an example mass spectrometry graph. On the y-axis, you always have percent abundance, which basically just means the amount or the number of atoms of that isotope. And on the y-axis, we have the mass to charge ratio. So think of this just as the mass. Since we have peaks at 90, 91, 92, 93, 94, 96, we know that this atom must have a mass around 90. More specifically, we also know that the most common isotope of this atom is the isotope with a mass of 90. So that helps us figure out, what elements that we're dealing with. What's practical about this technique is, let's say you think that you have sample that contains atoms of strontium, 88. You think this might be in your sample. Well, let's say you got this for your mass spectra. Since there's no peak at the value of 88, you know that you don't have any atoms with a mass of 88 in your sample. So it's a very helpful technique for us to look at more detailed information. Stoichiometry, calculations involving moles and atoms and whatnot. Just a quick refresher, 1 mole is equal to 6.02 times 10 to the 23rd particles, whatever those particles are, atoms or molecules. And we can convert between moles and atoms and molecules using this relationship. We also know that molar mass is the mass of 1 mole of a substance, which has the units of grams per mole. We can apply these concepts to a bunch of different problems. The new thing in AP Chemistry we talked about was limiting versus excess reactants. So remember, a limiting reagent is the molecule that gets completely used up in a reaction. All of it gets used. Whereas the excess reagent or the excess reactant is the molecule that you have extra of that's going to be left over at the very end. And we did a bunch of calculations where you have to figure out what is the limiting and what is the excess, and blah, blah, blah. A quick example is if you have, 8 grams of H2 and 16 grams of O2, how do you figure out which one's in excess? Well, you would need to convert each compound into the product. So 8 grams of H2, there's 2 grams of H2, 1 mole of H2, and then the stoichiometry is for every 2 moles of H2 that react, you make 2 moles of H2O. Once you solve that, if this value that you get is less than the value you get when you use 16 grams of oxygen, you know that hydrogen must be your limiting reactant because it's all going to get used up since you're going to make less product, less water, than you would if you made oxygen. And from there we could calculate what's in excess, etc., etc. So one last thing that we learned with this was something called percent yield. Remember the equation, the formula for percent yield is your actual, which is what you actually got when you did the experiment, divided by the theoretical times 100. Where the theoretical value, the theoretical mass of product you could make, is what you get from the stoichiometry. And that's the number that you would get and put in the bottom. This basically tells you what, how efficient was your reaction? Did you make as much product as you thought you could? So stoichiometry, brief overview, but the main new concepts we talked about were limiting and excess reactants. And we can do a bunch of conceptual problems with those as well, with diagrams, which we'll practice in class. STP, remember this stands for standard temperature and pressure. And you need to know these conditions, just have them memorized. The temperature, standard temperature, is 0 degrees Celsius, which is the same thing as 273 Kelvin. Standard pressure is 1 atmosphere, ATM, which you also need to recognize is 760 millimeters of mercury, mmHg, which is the same thing as 760 torr. Just units to be familiar with, recognizing those units as units of pressure should they show up in a problem. The other concept we talked about was empirical versus molecular formulas. So remember, an empirical formula is the most simplified form of a molecular formula. So you can have multiple molecular formulas, but you can only ever have one empirical formula. So for example, if you had these compounds, these are all molecular formulas, but the empirical formula is CH2 because it's the most simplified form of all these. The types of problems we involved using empirical molecular formulas were, let's say you run a sample and you find out that it's 56.5% carbon, 7.11% hydrogen, and 36.4% phosphorus. What do we do with this information? First, you assume that you have 100 grams because then we can just use these percentages as our masses. So if you have 56.5 grams of carbon, we want to first convert that into moles. So if you convert those into moles, you'd get 4.71 moles of carbon. And then if you did it for all the other compounds, for hydrogen, you'd get about 7.04 moles of hydrogen. And for phosphorus, you'd get about 1.18 moles of phosphorus. What do you do from here? We divide by the smallest number of moles. So we would divide everything by 1.18. And the numbers that we would get, 1, about 6, and about 4. So that tells us our ratio of these atoms in this empirical formula. So the empirical formula for this compound would be C4H6P. That's the empirical formula, not the molecular. But that's how we would do these type of problems. Main thing, empirical is the most simplified form. What would you need to do from here? Well, let's say we just said that the empirical formula was C4H6P. Okay? So let's say you had a compound with a molecular mass of 170 grams per mole. That means there's some compound out there that when you take the empirical formula and you multiply it by some ratio, the mass is equal to 170 grams. Well, what we need to do first is figure out what is the mass of this compound. So 4 carbons, so that's 48, 6 hydrogens, and phosphorus, 31. So that's going to give me a mass of 85 grams per mole. Now, this compound that we're messing with has a mass of 170 grams per mole. So, essentially, if I take the molecular mass, this is what you need to do, the molecular divided by the empirical, that gives you a ratio 2. That tells us I have twice as many of these atoms in the same ratio in order to make this compound. So the molecular formula for this compound must be C8H12P2. So that is a brief overview of the stoichiometry, atoms, molecules, content from Big Idea 1.